All right. The next exam 3 is on chapter 7 and 8. In chapter 7, we're going to cover gases, liquids, and solids. I know we've talked about them a little bit at the beginning, like what's the difference, but now we're gonna get into the weeds. And those are our subtopics. The authors of your book take a different approach than I've seen before. They start with the theory rather than with the laws that led up to the theory. So I'm going to do it the way they do it, and hopefully it'll make sense. But historically speaking, the laws that led up to the kinetic molecular theory, actually the kinetic molecular theory was applied to gases first, and then it was found to be useful for liquids and solids. So we'll start off with physical properties of matter. Remember the difference between physical and chemical properties. No? A property is a description of some characteristic of matter. And if it's a physical property, it doesn't speak to any type of potential change in the identity of the substance. If it's a chemical property, it's alluding to the possibility for a change in identity, like wood burns. These physical properties we're going to apply to matter, volume and shape. Right, that's fairly straightforward. Density, we've talked about that before. Compressibility. What do we mean by compressibility? It's usually applied to gases. Solids are definitely not compressible. You can't squeeze them into a smaller volume under pressure most of the time. Takes a lot of pressure. Liquids are generally considered to be incompressible. In other words, you can't squeeze this mass into a smaller volume, which would what? Increase its density. Although under extreme conditions, we do get compressed liquids. For instance, these oceanographers go out, take samples from different depths in the ocean. And they've taken samples of salt water at extreme depths, like 2 or 3 miles down, and measured the density. And they find that water is more dense at that depth because it's under extreme pressure. Gases, they're definitely compressible. And that's, we're going to discuss that in more detail when we get to the gas laws. Thermal expansion, you know about thermal expansion. If you walk on a concrete sidewalk, you're experiencing thermal expansion, right? You see those joints in the concrete, they're there for a reason. The ones that have the fiber inserted are expansion joints, so that as they heat up in the summer, the concrete swells and closes that gap, and it has some cushion there to keep it from cracking. The other kind, where you just have a score across it, are contraction joints. So in the winter, the concrete gets cold and it starts to contract, and rather than break just anywhere it wants to or at some weak spot, we put these scores in there. So if it's going to crack, it'll crack on that score. And then when it heats up in the summer, it'll close up again. That's thermal expansion. So I already mentioned this. Compressibility refers to a change in volume. So we haven't changed the identity of the substance, right? But we're not talking about chemical properties or chemical change. Thermal expansion is also a physical property. Some materials expand more than others for the same temperature change. It used to be when steel rails were laid for new track for railroads, they would be like maybe what, 12, 20 feet long, or maybe more. And then you'd have to tie them together, make a joint. And the joint would have a gap in it, especially if it was in cooler weather when you were laying it down. That way, when it heated up, it would expand and wouldn't buckle. It would have a place to go, expand and touch the other rail. Now they make steel that is almost incompressible, non-expandable. So that when it heats up, its change in length for a degree in temperature isn't that much. So now they can lay several miles of rail, just continuous rail, and not have to worry about expansion in the summer where it would want to buckle. Okay, so what distinguishes solids from liquids and gases in physical terms? This came straight out of your book. And if we're talking about the difference between solids, liquids, and gases, we can look at their difference in terms of volume, right? We can look at shape, right? We can look at density, which is kind of related to volume. And we can speak of them in terms of compressibility and thermal expansion. Okay, as a general rule, gases for the same mass, volume, same mass. We have to hold the mass constant in order to make volume make sense. For the same mass, gas is going to occupy more volume, much more volume. Right? So this is high, this is low, and this is very low. As a general rule, if a substance goes from a gas to a liquid, it shrinks. If it goes from a liquid to a solid, generally it shrinks some, not as much as from here to here. Shape, solids can hold their shape, right? This is, let's see, how do we express this? Definite shape. Indefinite shape. What that means is liquids have to have a container. Solids don't. And this is also indefinite shape. So gases and liquids have to have a container of some kind. Liquids can have a container that's open. So they might evaporate, but at least when you put them in there, you don't have to seal the top. Gases, you've got to seal. It has to be a three-dimensional container. If it's not, the gas will expand to fill whatever space is available. Density. Solids are generally high density, or I should say very high density. Liquids, by comparison, are just high or medium. And then gases are low density. That is for a given, and it relates to the volume. So for a given mass, you need more volume. And if density equals mass divided by volume, then if you have the same mass and you increase the volume, right, increase the denominator, the quotient becomes smaller. Compressibility. It's safe to say that solids are non-compressible. And we can say liquids are non-compressible in quotes. And these are definitely compressible. Gases are compressible. Thermal expansion is relatively low for solids. It's medium for liquids and high for gases. If you heat up a gas, it's going to expand, assuming the pressure is constant. Okay. So what does the kinetic molecular theory say, and what bearing does it have on these properties? Well, the kinetic molecular theory is the first postulate, I should say. Does anybody have math, geometry, and that kind of thing? Having to prove a theorem? No? Oh, okay. I guess they don't do that anymore. A postulate is an assumption that makes the theory work. So we assume that matter is composed of tiny particles, atoms, molecules, and ions. And we've actually been able to confirm that now. We've imaged them with some technologies. And these particles have definite sizes, and their characteristic sizes depending on what atoms they are, what molecules they are. Their complexity will make them bigger. And they don't change. These sizes do not change in any transition or any of these types of physical changes that may take place. The individual particles don't change. They're in constant random motion. Now, the only time that the substance does not have particles in constant motion would be what? A temperature of 0 K, absolute zero. They're not moving. That's by definition what 0 K means. Now, why do we say random motion? Well, if we had the computing power to follow every one of these billions of atoms or molecules in a small space, then theoretically we could predict the outcome of any changes we applied to them. Because we'd be able to say, all right, this molecule's going that way, this one's this way, that one's that way. They're going to collide and go this way. We don't have the computing power to do that, not even with the most powerful systems that we now possess. So we approach their motion statistically. And in order to do that, we just have to say blanket, their motion is random. We don't even try to track them. But since they each have size, they have mass, each particle has kinetic energy. And kinetic energy is defined. Has anybody had physics? I've asked you that before, haven't I?
Possible physics.
Okay, so you've probably seen this. Yeah. In order for something for kinetic energy is energy of motion. So if it's moving, it has mass and it's moving at a velocity, you can calculate its kinetic energy. And each one of these particles has kinetic energy. Now, they're not all moving at the same velocity, and they may not have the same mass unless it's a pure substance. In that case, then you can ignore the mass and say, we're only focusing on the velocity because all the masses are the same. But what we do is, since we say their motion is random and we can't track exactly what they're doing at any particular time, we say their average velocity times their average mass. Well, velocity squared times their average mass, take a half of that, and that's the average kinetic energy for the particles in the substance. And by the way, this value, if we're saying this is an average, and that's statistics, that means average. That average value is proportional to, that's what that means, proportional to their temperature. Okay, so that was the second postulate. The third is particles do interact with one another through attraction and repulsion, and that gives them a certain amount of potential energy, maybe on a microsecond scale, but it still transfers some of this kinetic energy to potential energy from time to time. All these particles are moving around, even in gases, even though they're very tenuous, so to speak. In just a sample that big, there are billions of atoms in that substance. And they may have a lot of space between them compared to their sizes. Like that would be a one atom over here, and that'd be another atom over there if we could expand it big enough. Whereas solids would be like this, and liquids would be kind of like that. So there's lots of space, but they still smack into each other, and they smack into the walls of the container. So for gases, since they hit the walls, then if we put a detector in there of some kind, a gauge, then they're also going to hit that gauge. And that's how we measure their pressure. Now, this potential energy, I forget, did we discuss that in this, the difference between potential energy and kinetic energy in here? Potential energy is stored energy. It's available, but it's not realized at the present time. Now, it can be, you can ascribe potential energy based upon an object's position in a gravitational field. Like if I'm on the ground and then I walk up the stairs and get on the roof, I've added to my potential energy based upon the expenditure of energy to get there. So energy is conserved always. In other words, all the energy in the universe is all the energy that's ever existed. All we do is just change it from one to another. So I would store up that energy to get to the roof. And then if I want to get that energy back as kinetic energy, what can I do? Well, I wouldn't advise it, but I could just jump off the roof. And right as I hit the ground, I would have all that energy back in kinetic energy. Now, of course, when I hit the ground, I lose that kinetic energy to broken bones and internal organ damage and whatever else, or heat. But that's one way that we store energy as potential energy. The other way is perhaps in a condition. Say if I take this rubber band, I have to put energy into it to stretch it, right? I've stored energy in that rubber band. And if I want to get it back, I just turn it loose. Okay. My brother and I used to have rubber band gun games, fights. We'd make a rubber band gun with clothespins. And my brother was younger than me. He didn't have quite the mechanical. So his would be this piece of wood with one clothespin on it. So he could hook the one end there and pull it back to the clothespin, and he's ready to go. Whereas I would have a piece of wood and I put a clothespin on the top and one on the side and one on the other side and have 3 notches in the front, and I'd be able to fire 3 times for every one of his. And that just made him mad. But I stored energy in that rubber band. Now you can also store energy in composition. Suppose you can look at it in 2 ways: physical composition or chemical composition. Physical composition would be something like heating a substance. Store energy as heat. And then you could get it back by just transferring that heat to some other location. Or chemical energy, we store that energy in chemical bonds, like nitroglycerin. We store energy in those bonds, and then all you have to do is look at it cross-eyed and it'll blow up. And you get all that energy back. So that's potential energy. Another type that's mentioned here is electrostatic. So if you have 2 positive charges and they come together, as they approach one another, they slow down because they're repelling, right? And right as they make contact, if they make contact, you stored up all their kinetic energy in potential electrostatic energy. And then, of course, they're going to fly apart and get that energy back. Or if they're positive and negative, then they're going to attract one another. And anything holding them back is going to be a storage of energy. Say they're together. Now we pull them apart like a magnet with a north and a south pole together. You pull them apart, you can feel them straining. You're adding energy to get them apart. And then if you don't go too far and just turn them loose, they'll go like that. Rare earth magnets. Actually, you can buy them on the internet now. It's little things. They have little posts on them, so you can put them on your refrigerator. Tack notes up there. Their interactions are very short range, but they're extremely strong. So if you have one of those, if you have a bigger one of those magnets and you get too close to the edge, and your finger happens to be in the way, it's going to get pinched and you're going to feel it. So there's a very strong attraction there. That's actually magnetic interaction, not electrostatic, but the idea is similar. Now, one thing when we're talking about interactions of individual particles in this theory, they can have, say if it's an electrostatic attraction, say one molecule has a positive side and a negative side, and its neighbor, same way. If they orient properly, then the positive and the negative is going to attract if they have a permanent charge. But what we discovered, and the theory has to accommodate, is that even neutral atoms and neutral molecules that have no permanent charge will attract one another. So how do we account for that? Well, it has to be temporary. They have temporary charges. Right? Where do those charges come from? Well, at the atomic level, you have protons and electrons in the atoms, right? Well, the electrons are out here moving around. Maybe they just, for an instant, they're more on one side of the molecule or the atom than the other side. That for an instant gives you a separation of charges. So you have a positive and negative. It doesn't have to last very long to see the effects. For instance, nitrogen gas. That's obviously, we say non-polar. It doesn't have a negative side and a positive side. Because you've got two same atoms here, they're equally pulling on electrons. They have certain attraction for electrons, and they're bonded together. So this is a completely non-polar molecule. But if we cool it down to minus 195 centigrade or Celsius, then this gas will become a liquid. How do you account for that? One of the differences between gases, liquids, and solid is not just how close they are together, but the attraction that holds them together. Because if there's no attraction holding this solid together, they just fly apart. Same for the liquid. There's even some attraction in the gases. It's very small, but it's there. So how do we get this to go from gas to liquid? There has to be a temporary separation of charges. It doesn't have to last very long, but it's long enough so that if we make it cold enough to where the kinetic energy of the moving molecules doesn't overwhelm the attraction, that's what happens, then we remove that kinetic energy by cooling it down, and now it's cold enough to where the attraction, this temporary attractiveness takes over. And that's how we get gas to liquid for a nonpolar substance like that. Okay. I mentioned this one already. the average kinetic energy of a substance is proportional to the temperature. Now, we're not saying that there's a formula that will relate the two. We're just saying that as the temperature goes up, the average kinetic energy of the particles goes up, and vice versa. The collisions, we said that there are interactions between the molecules, but for the theory itself to work, our starting position is that these particles in our substance, they act like billiard balls when they hit each other, right? There's no discernible attraction or repulsion as they come together and bounce off. That's part of the kinetic molecular theory. Now we know then once we have that in mind, then we add our tweaks. Like maybe they're a little slightly attractive or they're slightly repulsive. And we work from that central position of no attraction, no repulsion to reality. And the kinetic energy is conserved. Okay, how do we explain the difference between solids, liquids, and gases in terms of this theory? Well, the authors of your textbook have proposed a balance between potential energy and kinetic energy. Ran out of WD-40, so it's going to be kind of hard to erase that board. So kinetic energy is viewed as a disruptive influence. Okay. Potential energy is viewed as a cohesive force or influence. Disruptive. Yeah, I spelled that right. So if we look at it that way, then and look at the difference between solids, liquids, and gases, and try to envision a balance between these two forces, potential energy and kinetic energy, where do we have a balance between the two? Right here, middle. Disruptive is approximately equal to cohesive. Whereas with gases, the kinetic energy and the disruptive forces are greater than the cohesive forces. That's why we can study gases irrespective. Gas laws were studyable in earlier centuries, because if the disruptive force is so great that it overcomes cohesive forces, any cohesive forces that might exist among molecules are insignificant. So you can study gases as if they're all the same. And we'll get to that when we talk about gas laws. And then over here, the disruptive forces are less than the cohesive forces. So that's the general understanding of solids, liquids, and gases in terms of these two competing forces. Okay, this just in black and white says what I just told you. For solids, cohesive wins over disruptive. The particles in a solid are drawn together, often, not always, but often in regular patterns by these cohesive forces. So you can have crystalline solids. I spell that right? I think so. Crystalline solids. Or you can have amorphous solids. Crystalline solids have a regular repeating structure. We call it the unit cell. Amorphous solids just, they're solid. Yeah, I mean, they have the characteristics of fixed shape and high density and but they don't have that regular repeating pattern. A good example of that is let's see. Well, crystalline would be something like sodium chloride. Right? If you spill salt on a table and look at it, you see tiny little cubes. The regular patterns of sodium and chloride ions are arranged in there so that you get this repeating pattern. It makes a cube. Amorphous solids are like, I don't know, glass. Glass is amorphous. We treat it as if it was crystalline, but it's not. It's amorphous. In fact, some scientists study glass as if it's a supercooled liquid. It probably means something to them. Okay, so that's solids. In general, though, even if it's crystalline or amorphous, the individual particles stay put. There may not be a repeating pattern, but they don't move. They stay in their position, wherever they happen to be when they solidify. They occupy that fixed position. Now they can vibrate, heat them up, and they can start vibrating in that where they are. And if they vibrate like that, as you heat them up, they're going to need more elbow room, so to speak. And they get that elbow room. We see that expression of elbow room by thermal expansion. So as they vibrate, they tend to expand. Increase the volume, excuse me. Okay, definite volume, definite shape, right? High density, relatively high density. They get typically as close together as they possibly can for a given temperature. And very often when we're investigating particularly crystalline solids, we assume that they're shoulder to shoulder. They're like balls, shoulder to shoulder. The balls may be different sizes, but they still touch one another. And this unit cell I mentioned can be described in terms of where those balls are in that cell. Very incompressible. When you think of non-compressible solids, you think of, is there any empty space in there that can be taken up by compression? Right? For solids, there's not that much. There's very little excess space between the atoms, between the molecules. So solids, for that reason, solids are generally considered incompressible. Relatively small thermal expansion, although it is measurable. And the cohesive forces being very strong, at least at this short range, keep them from expanding too far. And if the cohesive forces, if we're comparing two solids and the cohesive forces for this solid are less than they are for this one, then I would expect the thermal expansion to be greater for this one. Because there are weaker forces that have to be overcome in order for it to expand. Liquids I mentioned before, the disruptive forces and the cohesive forces are roughly balanced. And the particles are randomly packed. They are definitely amorphous. They're free to move past one another. They're not locked in place. That's why liquids need a container. Because if they're not locked in place, then you dump the liquid out on a table and it's just going to go like that. The particles are free to move wherever they want to. All right, so there you got a liquid in a container and it's just, they're randomly positioned. And for that reason, they have an indefinite shape. The attractive forces are strong enough to hold them in a definite volume, but they're not strong enough to keep the particles in position to hold their shape. They have a relatively high density. In other words, for most solids, when you heat them high enough to make a liquid, their density doesn't change that much. Most solids will slightly decrease their density because there's a little bit more space added between the molecules as they're free to move. But it's not very much. Now, there are a handful of liquids that defy that. In other words, when you heat them up, their density increases. Water's one of them. If you take the solid, it has a certain density, and if you heat it up, its density goes up. And that has to do with the way it's structured. I don't know if I mentioned that to you guys before when we were talking about density. Maybe I did, maybe I didn't. I'll mention it again if it becomes important. All right, they have relatively small compressibility, although it is measurable under very high pressures. The reason that you don't have high compressibility in liquids is that they may be free to move past one another, but there's not a whole lot of space left. Even though they can move past, there's not space that can be taken up by pushing them closer together. And they have a relatively small thermal expansion. Now you can measure thermal expansion as linear expansion. And I mentioned that with steel railroad ties, steel railroad rails. You measure linear expansion. But you can also measure volume expansion. And that's the kind we measure for liquids, typically. I mean, you can still measure linear expansion for liquids. For instance, your thermometers, right? They've got that liquid in them. When you heat them up, you see that little, I guess it's red now or orange, that liquid start to rise, and it's calibrated for a different temperature. Well, that's a linear direction because it can't move in the other dimensions. It can only move in one dimension because it's confined by that capillary. So expansion itself occurs in 3 dimensions. There's no arguing that. But how we measure it can be different. All right, for gases, I mentioned the disruptive forces far outweigh the cohesive forces. So these gases the cohesive forces are almost non-existent. And they're very far apart, particles are far apart. So they don't feel each other, any cohesive forces, except when they come close enough together to interact. But for most purposes, you can treat a gas as if the cohesive forces are non-existent. For relatively high temperatures, and room temperature qualifies for that, relative to 0 K. What's room temperature in Kelvin? Well, standard temperature is 25. So 25 plus 273 is 298, right? So 298 K is considered high temperature as far as gases are concerned. So that's why at room temperature, all gases tend to behave alike for their physical characteristics, their physical properties. Or under low pressure. And see, I mentioned temperature, pressure. Yeah, low pressure, high temperature will give you common behavior for all gases. And these particles are essentially moving independently from one another, randomly moving. And they have to be confined in a space. So if we all of a sudden, well, I don't know, I'm trying to think of a good example, a thought problem. Say you have two bulbs with gas in one and a vacuum in the other, and there's a valve between them. If you open that valve, what's going to happen? That gas is going toward the vacuum, right? Lickety split. And it's going to go there and until the distribution of gas particles is uniform throughout. Right? I haven't mentioned it yet because we haven't talked about solutions in enough detail. But no, I better not. I'll save it for later. Okay, so this indefinite volume and an indefinite shape is due to the fact that these particles are randomly moving, they're very far apart, and the cohesive forces are almost non-existent. They're overcome by very high kinetic energy. In fact, you can, there are formulas where you can calculate the velocity of molecules in a gas. We're not going to get into them here. I think second semester general chemistry, we'll talk about that, but not in this class. Not enough time. Low density, right? So if you have the same mass, large volume, you're definitely going to have low density. Very compressible. And this compressibility is due almost exclusively to the fact that these gas particles are very far apart. Lots of space in between. So if you start decreasing the volume, they still got room to move around. I mean, we're pushing them closer together, but there's still a lot of room in there. In fact, an ideal gas is treated as if the particles are not even there. So you keep compressing it, you can compress it down to zero volume, and it's still a gas. There's no gas left. Now we know that's not the way they behave because they have mass, right? They have volume, but there's lots of space between the particles. And when you compress them like that, if you apply a force, then they're going to push back with equal force. Because if it's at the same temperature under low pressure as it is under high pressure, then all the molecules have the same kinetic energy and they're smacking against your piston, right? Now that you've pushed them into a smaller space, you got more particles hitting that piston with the same force. For each one, you just add up more force with more particles. So it takes more and more and more pressure to get them into a smaller volume because they're pushing back kinetically. Now, I'm not sure about moderate thermal expansion. I would say the thermal expansion for gases is high, especially compared to solids and liquids. So when you increase the temperature, you're increasing the average kinetic energy of the particles, and their masses are still the same, so that means their velocities have to increase. So as you increase the temperature, you increase their velocities and their kinetic energy, and when they strike the walls of the container, you have to apply more pressure to keep them from pushing the piston, or keep them from expanding. If you have uniform pressure, then as you heat them up, that gas is going to expand because it's pushing on that piston with more force. because it has more kinetic energy. All right. Now we get to the gas laws. So we talked about the theory. Now we're going to talk about the gas laws. And these, I think I mentioned early on, that generally speaking, science develops laws first. They describe the natural world in terms that are predictable. In other words, if this happens under these circumstances, that's the outcome. That's all a law does. It just says, if this, then that. Doesn't have to say why. We've already seen why with the theory. Now we're going to look at the gas laws and how they developed over time. The first one has to do with pressure. Oh, by the way, to physically describe a gas, you need to know 4 factors. You need to know pressure, temperature, volume, and N is moles. That is numbers of particles. Okay. If you know all 4 of those, then you can completely describe the physical behavior of a gas. So we need to get a handle on what pressure is. Well, pressure in physical terms, in physics, is simply a force applied over a given area. So it's force per unit area. That is an intensive property. Right? Because if you apply more force over more area, you get the same pressure. And we've got these units of pressure that have been grandfathered in from centuries gone by. So we have lots of ways to express pressure. One is simply saying, what's the force? And in SI units, force is in newtons, right? And area would be derived from length, which is meters, Newton per meter squared, right? That would be an expression of pressure, 1 Newton per meter squared. And in fact, this is given a value of 1 Pascal. Pascal was a polymath. I think he was French. And he did a lot of work with gases and pressure, all this stuff. So they named one of the units after him. We can also express pressure in terms of relative to atmospheric pressure. So at sea level, the average pressure, the atmospheric pressure at sea level is given 1, and everything else is related to that. So at our elevation, well, not here, but in Beckley, it's about 2,400 feet above sea level. Here, it's probably what? Well, Charleston is like 750 feet above sea level. So here, we're a little higher than Charleston here. We have to be because the Guyandotte River has to flow downhill, right? To meet the new river. So we're probably what, 850 or maybe 900 feet here, something like that. So at higher elevations, you get lower atmospheric pressure. So we're going to be less than an atmosphere at this location, and even less than that in Beckley. We can also express it. Now, these are metric units. If we express this in imperial units, pounds per square inch is an accepted value. Now, these are related also. So that slide shows you, well, one other one that I didn't mention is millimeters of mercury. All right, so I want to check my hard copies. I don't want to steal my own thunder. Yeah, it's coming up. Millimeters of mercury is related to the first barometer that was created by Evangelista Torricelli. And we have, remember, anytime you have an equivalence, you've got a conversion factor. So we can say that 1 atmosphere, let's see, let's move that out of the way. 1 atmosphere equals, let's see, what do they have first? 760 millimeters of mercury in the barometer. You ever seen a mercury barometer before? They're not too common anymore. In fact, this science lab doesn't have one. My Greenbrier campus lab has a mercury thermometer. It has a hanging on the wall, and it's got a reservoir of mercury in the bottom, and it's got a long tube with a scale next to it. And you read the height of that mercury to see what the air pressure is at that particular time, the barometric pressure. Well, we'll talk about that a little more in a minute. Torricelli, since he invented the barometer, we named a unit after him. So 760 torr is the same thing as millimeters of mercury. 1 atmosphere can also be, let's see, they're rounded it off to 1 decimal place, 14.7 pounds per square inch. All of those are valid. So any one of these can be used as a conversion factor, right? This is equal to that. So if you have units of atmospheres and you want to change it to pounds per square inch, you use that 1 atmosphere per 14.7 pounds per square inch. All right. Now, strictly speaking, kilogram per square meter is not force per unit area. Kilogram is mass. It's not a force. So the force is actually newtons. And it's newtons because it's derived from Newton's second law of motion. Force equals mass times acceleration. Right? So a 1 Newton force has a mass of 1 kilogram. And this force applied to 1 kilogram will make it accelerate at 1 meter per second squared. So kilogram meter per second squared is 1 Newton. If you have a calculation where you need to be able to cancel units, then instead of a Newton, you would use kilogram meters per second squared. All right. So this pressure is exerted by the gas on its container. And it's an intensive property. So any pressure, that pressure of that gas, as long as you don't change any of the factors, you don't change the volume of the gas, you don't change the temperature, you don't add any more gas to your container, then it will have that constant pressure. Now here's Torricelli's barometer. He, let's see, this was in the 1600s, I think. And glass blowers had become very good at making glass items. One in particular, a long tube of a uniform diameter. And in fact, there were scientists that could do it themselves. So for all I know, Torricelli could have made that tube himself. Or he could have just bought it from somebody and taken that tube and sealed off one end of it. So first of all, the tube would be like this, right? And he would fill it with mercury. Now, why did he use mercury? Because of its density. He could have used water. And maybe he did try water with some of his early attempts. But if you use water, instead of a tube this long, for 1 atmosphere pressure, you would need a tube at least 33 feet long because of the difference in density, right? Mercury is about 13.5 times as dense as water. So mercury made more sense. We had filled it with mercury, and then he had this vat of mercury here. Right? And he put his thumb or his hand over the end, and he inverted it and submerged his hand in the mercury. They didn't know about mercury poisoning back then. And when he took his hand off, the level of mercury dropped. See up there at the top, the level of mercury dropped, but it didn't go all the way down to the surface. Right? It stayed up. So he reasoned what was holding that mercury up. There was nothing pulling on it from above because there's nothing in that space. That was the first vacuum. Right? If there's matter there, 1 second, and the next second there's no matter there, that's a vacuum. So he created a vacuum. There's nothing pulling on the mercury, so it had to be a push. And he reasoned that it was the atmosphere, the gases in the atmosphere of a certain height. They didn't know exactly how high then, but it was very high, miles high, was bearing down on that mercury, applying pressure to the pool of mercury and holding that column up. And he noticed that if he took that invention and put it in the back of his ox cart and went up the mountain, the level of mercury dropped because there's not as much air above him now. Or if he went down to this beach by the sea, the level went up because there's more atmosphere bearing down on that pool. That was one way that the barometer was used. Another way was once the barometer was invented, some adventurous souls, well, not adventurous, I guess, because you just take the barometer and sit it on your desk and leave it there and watch it change over time. And they noticed a correlation between high level with good weather, low level with bad weather. And we still see that today. Low pressure or a dropping barometric pressure means bad weather's on the way. Low pressure system. And we still measure air pressure for those air pressure systems all over the world. And we have these hurricane chasers, these planes that fly into the hurricane. They drop these sonobuoys out the bottom of the plane and sends back data. And one of those data streams is pressure, air pressure. You measure the air pressure of the hurricane. The lower the pressure, the stronger the hurricane. And I looked it up. I used to know the lowest pressure ever measured in a hurricane is like 870 maybe millimeters of mercury. Right. And that's at sea level. So that's a difference of, no, not 800. Hold on a second. There's another unit of measure that I didn't mention. It's the bar. Now, not on the top of my head, I can't remember what the conversion is, but that's the millibar, or 1,000th of a bar, is what meteorologists use. Okay, so roughly 1,000 bar is 1 atmosphere. I think it's a little more than 1,000. So by comparison, inside the hurricane, it's down below, it's in the 800s. That's very low. And the lower, the stronger the hurricane. Okay, so these are the 4 variables that we're going to look at in for the gas laws. Robert Boyle was an Englishman. And let's see if this works better. Yeah. That's okay. And it was maybe, I don't know, maybe 30 years after the barometer was invented that Robert Boyle did his experiments with pressure and volume. So he wanted to see, how does pressure vary with volume? Now, if you want to investigate the relationship of two of these factors, the other two have to be constant. So that means Boyle would make this one constant and this one constant. And what he did was, he took one of those tubes and he bent it into a J like this. Okay? And he started adding mercury to it. Now, he also had a barometer over on the side. You can measure the air pressure. And as he added mercury to it, it pooled up in the bottom like that, right? Keeps adding to it, adding to it. When it touched the inner curve, now this is constant. He has sealed air in there, and there's no more going to get into it. So this is constant. This experiment takes just minutes to do. So the temperature is not going to change that much. And he noticed that as he added more mercury, he might add this much mercury overall, but over here it would only be there, up to that level. So he reasoned that there was something in there pushing back. And the gas was pushing back on the mercury. And the difference here, let's see, right, is the height, the difference in height between the two mercury columns. And the pressure on this gas in here is a combination of that difference in mercury, millimeters of mercury, plus atmospheric millimeters of mercury. So that's why he had a barometer on the side. He could add that together with this and get a total pressure on that gas. And then the height of this column, the H, is a measure of the volume because the tube is a uniform diameter. Right? So the height was a variable with the volume because the area didn't change. Remember, what's the volume of a cylinder? Height times area, right? Okay. So what he came up with was Boyle's law. Boyle's law simply said that if you measure the pressure of a trapped gas times its measured volume, it's equal to a constant value. And this isn't very useful. I mean, it's true, but it's not very useful. What we need is a way to say, all right, if it's pressure volume under these conditions, what if I change one of those? Right? Can I find out what the other one is? Well, yeah, because this measured pressure here equals that constant. But say you change the pressure to a new value. Now you get a new volume, and that's equal to the same K. Okay? So now that's why that formula works, because this A is equal to B is equal to C, A is equal to C. So P1V1 equals P2V2. This is an inverse proportion. Anytime you have two variables times each other equals a constant. Product of variables equal a constant is an inverse proportion. Because if it's a constant and one of them goes up, the other one has to go down. There's no way around it in order to keep that constant. Okay, this is what I call before and after. If you know before conditions, if you know this one, you know that one, then you change the pressure to this one, you've got a a formula with 4 variables, and one of them is unknown. You can solve it. Right? Any equation with one unknown, we can solve it. So that's why I call it before and after. You know the before conditions and some of the after conditions, missing only one, you can solve it. This is an expression of, say we have 100 millimeter mercury pressure on 8 liters of gas, and we increase the pressure to 200. Now we're going to have 4 liters. If we increase it to 400, we're going to have 2 liters. All right. That's the correct mathematical expression for Boyle's law in the before and after scenario. So let's see, 10. Oh, we're good till 1. If helium gas occupies 12.4 liters at 23 degrees and 0.956 atmospheres, what volume will it occupy at 1.2 atmospheres? All right, for these types of problems, if you want to know that it's a before and after situation, you look at what's given. You're given 12.4 liters. And that's before, and you're asked, what is it after? So your before volume is 12.4 liters. Your after volume is unknown. Your before pressure related to that 12.4 liters is 0.956 atmospheres. You're changing the pressure to what? 1.2 atmospheres? Okay. Now we have to say that the temperature is constant at 23 degrees, and we know the number of moles is constant because the gas is continuously trapped. We're not adding any gas, we're not taking any away. So now that you have it in this format, it's easy to plug those numbers in to our formula and get the right answer. 9.88 liters. Now, does that make any sense? 9.88 liters. Well, if we go from this pressure, increase the pressure, the volume should decrease. Okay? Reasonable. Next, gas law. Let's see, maybe this works better. The next gas law had to wait about 100 years for the invention of a thermometer. The barometer was invented first. A reliable thermometer and a scale for that thermometer was invented. Well, we had actually several. The one we're interested in is Celsius. And that thermometer became available. So Charles, who was a Frenchman, wanted to investigate the relationship between volume and temperature. Temperature and volume. That means pressure has to be constant and moles has to be constant. Okay. So how did you do that? Well, the easiest way is to create a device with a sliding piston in it. We got a piston right here. Right? So we've got a volume in here at the beginning. And we have a uniform pressure here. All we need is just to add some weight to it and make sure that that's constant. So let's just say we just add a 1 kilogram stone on top of it. So the pressure is constant. We've trapped the gas in here, moles constant. Now we change the temperature. Right? So all we have to do is change the temperature surrounding the device and wait for it to equilibrate. Now the temperature inside is the same as the temperature outside. And we have our thermometer in here measuring the temperature. Okay, so this volume 1 is at temperature 1. What happens if we increase the temperature? The kinetic molecular theory says these molecules are going to start moving faster. And they're going to bang on that piston harder because they got more kinetic energy. So if the pressure here is constant, then they're going to push that piston up until the forces are balanced again. So now we're going to get, let's make it bigger. Now we're going to get, or we could decrease the temperature. Let's do that. Now the piston's down here. So now we have a new volume, volume 2, at a different temperature, temperature 2. Charles found that the relationship was direct. As you increase the temperature, the volume increases. So that would be V over T equals a constant. If you have two variables in a quotient equal to a constant, then they are directly proportional. As one goes up, the other goes up. They have to keep this constant. And the same situation holds here. If this is before and this is after equal to the same constant, then that one is equal to this one. Now, there's one kink in this story. If you measure, you can measure the temperature in Celsius, that's fine. But what happens when the temperature goes negative? Drops below 0. If you try to put the temperature in there as a negative, then you don't have the equality anymore. So what we need is a temperature scale that has no negative numbers in it. They're always positive, and that's Kelvin. So with this relationship, when you have temperature in these gas laws, temperature has to be in Kelvin because there's nothing below 0 in Kelvin. Then it works. All right, that's just an illustration of what happens. All right, so before and after, we have a balloon containing 1.3 liter air. So volume 1 equals 1.3 liter. And at 24.7 degrees, so volume 1 at 24.7 degrees C. And we put the balloon in, that's not right. Liquid nitrogen is minus 195. That's closer to dry ice, minus 78.5. Now, possibly that temperature is in the vapor above the liquid nitrogen, right? If we want to really stretch and rationalize it. But the temperature now is down to minus 78.5 degrees C. We want to know what the volume is. Before we can use that data in this equation, we have to add 273 to each one to make Kelvin. Then you can plug the numbers in. And that's what it would look like. So naturally, if we decrease the temperature, the volume is going to decrease from 1.3 to 0.8 liters. All right. Well, there we go. Oops. All right, before we get to this combined gas law, there's one law that's missing. And I'm not sure why the authors omitted it. Maybe they figured there wasn't enough time or space to talk about it, but I'm going to talk about it. So in this case, we're going to hold this one constant and this one constant. We're going to let these two vary. What happens to volume when you change the number of moles? This is Avogadro's law. Now, Avogadro was an Italian, and he proposed the relationship here, but he didn't actually do the experiments. He was given credit by subsequent researchers because they were basing their research on his work. So they gave him credit for this law. And all it says is that when you relate volume to number of moles, that's a constant. You increase the number of moles, you increase the volume, as long as the pressure and temperature remain the same. So we get another one here, 1, 1 equals 2, 2. Okay? Avogadro actually said this. He said you have two gases. Have I done this one before? No. Okay. You have two gases, and it doesn't matter what the gases are. It's irrelevant. In this one and this one, the difference between the two is they have the same volume. They're at the same temperature. And they're at the same pressure. If all these are the same, then this one must be the same. If those are equal, then the gas in this one and the gas in that one must have exactly the same number of particles, same number of moles. Now, if you have two different gases, say you have, I don't know, CO2 in this one, and you have hydrogen in this one, they're going to have a different mass, right? Like this one, this mass 1 is going to be greater than mass 2. So this Avogadro's law and the work that he did and the researchers subsequent to him who used his information, one of them was his student, his name was Cannizzaro. This solved massive problems that chemists were having all over Europe in the mid 1800s. They had chemical reactions. Companies were depending on these reactions to produce a sellable product. Researchers were depending on reactions to discover new things and publish papers. And when something went wrong, they didn't know how to fix it because their relationships in reaction parlance was mass-based. It said certain mass of this reactant with a mass of this reactant produces these products. And when it didn't produce what they wanted it to, they had no way to figure it out because they didn't realize it's not the mass that reacts, it's the number of atoms that react. And this gave them a handle on it because now, if you have the same number of particles here and here, but they're different masses, then you can find out what the average mass of each one is, right? The difference between this one and this one is the difference between the masses of the individual particles. And once the light bulbs went on all over Europe then. And in fact, Mendeleev was working on his periodic table, and he used this information to help him build his table. We haven't talked about the periodic table yet, have we? Have we? That's what I get for teaching so many different courses. I can't even remember what I talked to you guys about. Maybe we did talk about the periodic table. Yeah, I'm pretty sure we did. Because it's not coming up. Yeah. Anyway. So now we have these three laws. And they're useful as long as you're sure that two of these factors are held constant, you can use the law, respective laws for the other two. But suppose you've got more than two variables in your equation. Right? Your before and after situation allows three of these things to vary. Right? How do you deal with that? Well, that's where the combined gas law comes in. Now, your authors only give you a combined gas law with pressure, volume, and temperature. But if we start with Boyle's law, we say P1 times V1 equals P2 times V2. Well, we also know that Charles' law says that volume and temperature are related. That right here. If pressure is constant, then you got Charles' law. Okay. So this is the equation that they gave you there, but we also know that volume and moles are related. So the true combined gas law has PVNT here and PVNT there. Okay. So in this case, you still have to have an equation where you know all the values except for one. Otherwise, you can't solve it, right? Anybody who's had algebra? You solve two simultaneous equations. You can for two unknowns. You have two unknowns. But if you've only got one unknown, one equation is all you can deal with. All right. So combined gas law, well, that's their expression of combined gas law. This is mine with moles added. And the reason I want to add moles is because of where I'm going with it. I'm going from combined gas law from a before-after situation to a state situation. Suppose you're in a situation where you only know the condition of your gas right now. You don't know how it got there, but you want to solve the problem for a given one of these parameters. Right? There's a way to do that. If we know this first, well, here's an example of one where we have several variables. And we're going to find out what's at what temperature does 121 milliliters of CO2 at 27 degrees, 1.05 atmospheres occupy a volume of 293 milliliters at a pressure of 1.4 atmospheres. We have to solve the equation for Kelvin, right, to convert all the temperatures to Kelvin, and then solve it for the unknown temperature, and then convert it back to Celsius. So once you get Kelvin, just subtract 273 from it, and you got your temperature in Celsius. All right, here's the ideal gas law. The ideal gas law allows us to solve a state function, not a before and after function. We only know how we got there. Notice that all of these laws are equal to a constant. So this is equal to a constant. Right? Both of these are equal to the same constant. So if we just take one side of it, right, and say it's equal to that constant, PV over NT equals our constant. If we know what that constant is, and it will have certain units assigned to it, and these are expressed in the same units as the constant, then we've got the makings of an equation that will allow us to solve for a state situation. All right. If we say pressure, what would happen if we had gas at 1 atmosphere pressure? And we're talking about 1 mole of gas. at a standard temperature, and standard temperature for gases is 0 degrees Celsius. And so that's 273 K, right? 0 plus 273. What would the volume be? Well, the volume that we measure under these conditions is 22.4 liters. Now we have values for these, and we can find out what the K is. In this case, it would be 0.08206 liter atmosphere per mole K. So now we have a constant. As long as we use atmospheres, liters, moles, and K temperature, we can use this value for the constant. And in fact, the constant is given a special letter. That's the ideal gas constant. Now they rounded it off to 821. I like 8206. But for our problems, probably 821 ought to work. Right. Okay. These are considered standard conditions. Pressure of 1 atmosphere for 1 mole of gas at 0 degrees Celsius or 273 K. Those are standard temperature and pressure conditions. All right. So here's a condition. Now, how do you tell if you've got a before and after or a state situation? So you can use the right formula. Well, you look at the problem and say, all right, do I have pairs of values for these? If you got pairs of values, then before and after is probably your best bet. If you don't have pairs, if you just have single values for each one of these, missing one of them, of course, then you use the state function or the ideal gas equation. We want to know the number of moles of air in the tire. If the tire is at 23 degrees and the volume is 25 liters and the pressure inside is 2.18 atmospheres, which is equivalent to 32 pounds per square inch. I don't know about that. My tires are recommended at 35. I mean, right now they're in this cold weather, they're down to 32. But that just means I have to add some more air to them. Okay. So that's the way you will see the equation most often. PV equals nRT. Pressure, volume, moles, temperature, gas constant. And if we solve for moles in this case, we find that inside that tire, we have 2.24 moles of gas, of air. Okay. Another example. What's the pressure inside a 304 liter tank that contains 5.67 kilograms of helium at 25 degrees? We can't use kilograms in this formula. What we have to do is change kilograms to moles. And since we know that the gas is helium, we can change it. We can change to moles, right? You know how to do that. Molar mass of helium, 4.0 something, 4.02 maybe, I think. I can't read that far. So we're looking for pressure. Volume is in liters. The units of R dictate the units of P, T, B, and N. So if you're using 0.08206, you have to have liters for volume, pressure in atmospheres, moles, and temperature in K. Now, there are other units applied to the gas constant, depending on, in fact, it's spread. The use of the gas constant has spread through other parts of physics and chemistry. So you may see it different ways. Like if we had units of joules per mole K, that value would 8.3145 would be that value. So if you change the units, the number's going to change. So you have to be sure and use the right units. For our purposes, in these gas equations, the gas equation, we're going to use 0.08206. And we find out that if we change kilograms to 4.003, if we change kilograms to moles, that's what 5.60 times 1,000 divided by 4. That simply says 5.670 kilograms. Right? And that parentheses in there is incorporating, right, kilograms on the bottom, 1,000 grams on the top, and then we get rid of grams per mole by 4.003. There, okay, grams. So that's why you have 5.6 times 1,000 divided by 4 inside those parentheses. That's where it comes from. And then we calculate the pressure inside that tank. 114 atmospheres. Do you realize how much pressure that is? That is massive. That's why these compressed gas cylinders you want to handle very carefully. Okay? If you ever do that and you happen to drop one, it tips over. If it just hits the floor on its side, it's probably okay. But if it falls and the stem strikes something on the way down, you're going to have a missile on your hands. I haven't seen it personally, but I've seen videos of a gas cylinder laying on its side, and they purposely wanted to see what would happen. So they set it on its side, and they put a target out here. It was like layers and layers of, no, it was a cinder block wall. That's what it was, cinder block wall. And then they had this guillotine type thing, and they got way, way, way far away from it behind protection and tripped it, and it knocked the top off, and that cylinder went through that wall like it wasn't even there. Those cylinders are pressurized. The big cylinders, the K-size cylinders, are about 2,500 PSI. So let's see, 2,500 PSI would be how many atmospheres? 14.7. That's 170 atmospheres. So this one is a little less. Maybe we used some of it already. Okay. So those were the main gas laws, and they came, historically, they came first in that succession. Boyle's, followed by Charles, followed by Avogadro. But then John Dalton was also working, most scientists were at this time working in this area. And Dalton noticed that if you have a mixture of gases, that he could predict the total pressure of the gas if he knew the individual pressures of the gases that were in the container. Right? So Dalton's law of partial pressures simply says that the total pressure is equal to the arithmetic sum of all the individual pressures of however many gases are in that container. So each gas exerts its own pressure as if the others weren't even there. That's what he's saying. And if we relate that back to the kinetic molecular theory, right? This gas has its kinetic energy. This gas has its kinetic energy. And if it's by itself, it will exert a certain pressure, right? Because it's striking the walls of the container. This one by itself will do the same thing. But if we put them together, This one is applying its pressure. This one is applying its forces for each of the particles. This one's applying its forces for each of its particles. They add together. And they make the overall pressure. Okay, let's see. Sample problem. A gas mixture containing oxygen, helium, and nitrogen has a total pressure of 780 millimeters of mercury. 780 millimeters of mercury total. Okay. What's the partial pressure of oxygen? So if we have this one, oxygen is our unknown, and then helium is 86 millimeters of mercury. This is helium. And nitrogen is the other one at 124. Yeah. 124 millimeters of mercury. This is nitrogen. Then we have an equation in one unknown. Okay. Simple. That should be 570 millimeters of mercury. Now, let me see how far we're going to carry this. Oh, that's reserved for general chemistry. But just so that you're not completely ignorant at parties, the ratio of these pressures, like 570 to 780, is the same ratio as the mole ratio. So if you have the total moles here, let's say you have a total of 1 mole of gas, gives you that pressure. And it's a mixture of these two. You can find out how much of that 1 mole is oxygen by this ratio, 570 to 780. Right? And that'll tell you how many moles of oxygen is in that container. Okay. This, by the way, is equal to, that's known as the mole fraction. It's just information. I don't think I've got that. That's not going to be on a test. Okay. So now we're presented with this problem. Where we have 2 bulbs containing gas, and there's a valve between them, and they're maintained at 45 degrees Celsius. So the temperature is constant. And one side has 2 atmospheres and 9 liters, and the other side has 3 atmospheres and 3 liters. So let me draw that picture. See, they're connected by a valve. And let's put the smaller one on this side at 3 atmospheres and 3 liters. And the bigger ones on this side at 2 atmospheres and 9 liters. Okay. The question is, what happens when you open that valve? What's the pressure of the gas, the total pressure of the gas when you open that valve? What we need to know, if we want the total pressure here, we know that this is 2 atmospheres and that's 3. So which way is the gas going to move? Going that way, right? Until it equilibrates. So the pressure is going to be somewhere between 2 and 3. 3 is going to go down, 2 is going to go up. Right? We know that qualitatively, the pressure is going to be between 2 and 3 atmospheres. But in order to use Dalton's law of partial pressure, we need to know what's the partial pressure of this one after you open the valve. And then what's the partial pressure of that one contributing after you open the valve? Then you can add them together to get the total. Well, here's the trick. Set it up so you run the experiment twice. The first time you do it, that's a vacuum. Open this and it goes in here, equilibrates. What's the pressure in that due to this gas with our new volume? Then you back up, make that a vacuum, and open the valve. What's the new pressure over here? Because we know the volume. We know the volume. So the total volume is known. The beginning pressure, if this is a vacuum, the beginning pressure is 3. Now it's going to be something less than 3. So we use Boyle's law twice. Once for this side with a vacuum, once for that side with a vacuum. Then we add them together. And we can find out the total pressure. Okay, let me see it. Do I have it worked out? Yeah. So in this case, the final volume is going to be the same for both of our experiments, our thought experiments. 12 liters is going to be the final volume. The initial volume depends on which one is the vacuum and which one's got the gas in it. So if we say gas 1 is 2 atmospheres and 9 liters, we're saying that the green side is now a vacuum. Okay? And that box is supposed to be a dot. So we solve this using Boyle's law, and we find out that the contribution of this side to the total is 1.5 atmosphere. Then we turn it around, and we say, now this is the vacuum. Open the valve and solve the problem for the right hand, the green gas. And it contributes 0.75. Now use Dalton's law of partial pressure, add them together, and the final pressure is 2.25 atmosphere. So it is between 2 and 3. Okay. If this were, well, since this slide set is made for just this class, I don't use it anywhere else. It must be, I put that in there probably because at some time in the past, I did this lecture on a day when we had an exam. So you had the exam and there wasn't enough time left to do the whole thing. So I chopped it off there. But since we don't have anything else to do today, we could take a break if you want, come back and finish it. Or is everybody going ahead and taking their breaks on their own? I think that's probably the case. That way we can finish early. As soon as we're finished here, we're done. All right. So now that we're done with the gas laws for now, we'll use them later. Change of state. So a change of state is simply a physical change of some substance from gas to liquid, liquid to solid, gas to solid, or reverse any of those. Right? You're just changing its gas, liquid, solid state. Usually it's accomplished by one or more heating or cooling or pressure change. Sometimes both at the same time. These are terms we use for the different state changes. Freezing, condensation, deposition, melting, evaporation, sublimation. I'm going to show you what each one of those means. Let's see. All right, we could do that. But I like to put them in a triangle. So let's say, I'm going to put my, okay, gas is the lightest, so we'll put it at the top, right? So we got a gas up here. And this is the same substance. It's going through these different phase changes. And we've got a liquid over here. And we've got the solid over here. So if we go from a liquid to a gas here, this is known as evaporation. Or, and heat is absorbed. Right? Heat absorbed in order to make that transition. If it happens at 1 atmosphere pressure and there's enough heat absorbed so that you convert the liquid to the gas, we're talking about boiling. Okay? So what happens if we go the other direction from gas to liquid? This is called condensation. And heat is terminology released. Okay, we'll use their words. Released. Okay? What if we go from liquid to solid? Let's see, that way, that way. Let's go this way. Liquid to solid. That is freezing. And if we freeze it, heat is released. If we go the other direction, that's called melting. Yep. And heat is absorbed. Okay. The last one is between gases and solids. So let's see, my arrows are going this way on the outside. Say going this way. Gas to solid is deposition. And in that case, we're releasing heat. And the other way is like dry ice. This is sublimation. And in this case, heat is absorbed. So those are the 6 possibilities for phase changes. Deposition is interesting. And it's used more often than you might think. For instance, I was curious recently about how the James Webb Telescope was put together. So I focused in on those hexagonal sections. You know what the James Webb Telescope is, right? Okay. It was made, it's a huge mirror that was sent out to the Lagrange point beyond the moon. So it's out there in that position, relatively constant position. But it's away from interference from Earth and moon because it's an infrared telescope. And infrared works best when you can keep the detectors very cold. You don't have interference. So it's got sun shields on it below the mirror. They pointed toward the sun to keep it very, very cold. Well, those mirrors are ground to certain specifications so that when they open up, right, it has to be packaged to put it on the rocket, and then it opens up, and then each of those mirrors is individually controllable in that array. But what are they coated with? The best reflector for infrared radiation is gold. So they coated this section, this mirror, like that with gold. And it only took like just not even the size of my fingernail, just a tiny amount. They put it in this vacuum chamber and they heated up the gold in the device with the mirror sitting below it, and they masked off part of the mirror that they don't want to coat. And they sublimated the gold. right? They changed it from solid to gas with the heat and the low pressure. And the gold started drifting down under gravity, right? And that settled on the surface of the mirror. And at that point, it went the other direction. It went from gas to solid deposition. And they coated the mirror with just a very thin layer, right? That tiny amount of gold spread out over that whole mirror was all it needed. And then, of course, they put a protective coating over that so they wouldn't get scratched or deteriorate over time. Now, they do the same thing for amateur mirrors for telescopes, except they don't use gold. I think they use aluminum is common for visible light. All right. So when heat is absorbed here, here, and here, heat is absorbed for evaporation. Heat is absorbed for melting. And heat is absorbed for sublimation. This is called endothermic. We're adding heat to the system. For freezing, condensation, and deposition, condensation and deposition, this is exothermic. So to go back to the kinetic molecular theory, what's happening here? With evaporation, the phase change is adding kinetic energy to the particles. And that kinetic energy has to come from somewhere. And it comes from adding energy to the substance. Endothermic, we're adding energy to it. That's what makes it able to do that. If it goes the other direction, where the particles are actually slowing down, then it has to give that energy up. All right. I don't think we need to spend a lot of time on this. Everybody has an idea of what evaporation means, right? Liquid to gas. And in terms of the molecules, if it goes from liquid to gas, they're gaining kinetic energy, which means we have to add energy, endothermic. We can talk about rates. So the rate of evaporation increases with temperature. If you increase the temperature, you'll evaporate faster because you're adding all the energy it needs to transition from liquid to gas at a higher rate. More energy, faster evaporation. If you happen to put a liquid on a surface and let it evaporate, where is it getting that energy? Most often it's getting it from the surface it's sitting on. So the surface becomes cool, right? As you add energy to evaporate, it comes from that surface underneath. That's why when you have, especially if you get out of a pool on a hot sunny day, you've been for a swim, and you let the water start to evaporate, it will cool you down pretty quickly. So if it's actually a cool day, you may want to towel off first before you catch a cold. So that's the cooling effect, and some air conditioning systems, especially on large buildings, use this evaporative cooling, right? They transfer the energy to the interior of the building using Freon because it's more efficient transfer that way. But the cooling effect occurs at the evaporator coil on the roof of the building. And they've got water trickling down and fans blowing it. And as the fans blow and the water evaporates, it takes heat with it. And it cools the liquid that's inside the coiling, the tubes in the coils. Now, your household air conditioning systems don't do that because they don't need to. They just transfer energy from cold air and make it hot for the air conditioning mode. If it's a heat pump, you reverse the cycle, and now you got cold air coming out of the top of your unit outside, and the heat that's extracted there goes inside, which is the case these days. Let's see. So what do we notice about evaporating liquids? All right, we've discussed this part of it. Now, as a practical matter, if we allow a liquid to evaporate and it's reasonably volatile, like say we have a jar of crystal clear, 100% ethanol, it's going to evaporate, and you get close enough, you can smell it. So that ethanol is continuing to evaporate, and if we don't cork it, it'll continue to evaporate until it's all gone. But if we cork it, then we get some of that liquid escaping into the vapor phase. All right, it becomes a gas. And it keeps doing that until there's an equilibrium set up with the evaporation. Let's see. There's our cork. There's our liquid. Eventually, you get enough gas particles up here. So that's not a very good gas particle, is it? In the beginning, it's all one way. Liquid is becoming gas. But as you build up pressure, head pressure here, then you get more gas particles in the vapor phase, and you start to get enough of them going in the reverse direction. So you get evaporation and condensation happening at the same time and at the same rate. When that happens, then you have equilibrium. And you won't see the liquid drop in volume anymore. It'll stay the same. It's all about the rates. The rate of evaporation equals the rate of condensation. Then you have equilibrium. And then you have a measurable pressure, the vapor pressure, at a given temperature, at whatever temperature it is. It changes with temperature. That's the measured vapor pressure for any liquid. And it is an intensive property. Doesn't matter what size the vessel is, as long as you've got liquid in the bottom, and gas up here, and it's corked, for a given temperature, you'll have that same vapor pressure, no matter how much liquid you have in there. All right. That's an equilibrium, but it's a physical equilibrium. Now, you may guess that there's also example of chemical equilibrium, but we're not going to introduce that right now. It'll come later. Okay, so we observe no change in the volume of the liquid, but on the microscopic scale, the activity is furious. Evaporation, condensation, they're happening at unimaginable rates, but the rates are equal one way and the other way. And that gives you the vapor pressure. Now, the vapor pressure depends on temperature, but it also depends on the characteristic of the liquid. Like water will have a different vapor pressure than, in our example here, helium. And it all has to do with those attractive forces. Right? What are the attractive forces for water? Well, water H2O is like that. And the attraction for electrons is this way toward the oxygen. Okay, so the bond is covalent, but it's polar. So overall, we get a slight negative charge here and a slight positive on this end. So in the liquid phase, water orients itself so the negative is attracted to its neighbor's positive side. And that attractive force increases its boiling point, increases the amount of energy required to drive it into the vapor phase. So at any given temperature, compared to another gas, its vapor pressure is going to be low because the attraction in the liquid keeps it from moving into the vapor phase. Whereas helium is a very small atom, and it's nonpolar, obviously, because it's a single atom. But it doesn't even have a significant instantaneous charge that we mentioned earlier. So helium has a very high vapor pressure. At the same temperature, water would have a low vapor pressure because the attractive forces are so low for helium. In fact, the coldest substance we can make and keep in bulk is liquid helium. It's about 4K. Just 4K above absolute. That's the coldest. In fact, when superconductivity was first discovered, the conductive materials that were being used to test superconductivity had to be submerged in liquid helium. And then research progressed, and we found substances that would maintain their superconductivity at higher temperatures. And now instead of helium, we can use liquid nitrogen. So when you go to get an MRI, the doctor says you have to go in that torture machine and get an MRI. The magnets in that MRI machine are cooled with liquid nitrogen. You guys are going to need a copy of all this. Let me take a break, and because I don't want to carry these things back to Beckley with me. Let's see. I think I only have this one. I just got busy. I was having so much fun grading papers. I just forgot where I was. Let's see. Yeah. Okay. So we're a little over halfway through this chapter discussion. And fortunately, the internet's working today, so we've got a recording of it going. Do you have to go?
Yes.
Okay. We still have time. You just have to go, right? Okay. So vapor pressure. We talked about the difference between the attractive forces that hold the molecules together. The stronger those forces, the lower the vapor pressure. So as the strength of the forces increase, vapor pressure goes down. We often refer to some of those as volatile substances because they have very high vapor pressures at room temperature. And the EPA identifies them as VOCs. In any product that you buy, it'll have on the side, if it has volatile compounds in it, it'll have the VOC designation or percent. You know, how much or what does the vapor pressure do? I'm not sure what the units of measure are, but the volatile organic compounds are identified by law on that can of paint or that can of solvent. This particular one right here is dimethyl ether. It has a very high vapor pressure because it's a nonpolar molecule. It doesn't have a permanent positive and negative charge on it. It's very volatile. Okay. So we talked about physical equilibrium. Now we're moving on to boiling. The form of evaporation where the conversion of the liquid state to the vapor state occurs within the body of the liquid. It's not just at the surface anymore. It's usually, it happens at the point of heating. So if you've got a hot plate and you set water on your hot plate, you're going to see it boil from the bottom. And liquids boil when their vapor pressure reaches an equivalent to the external pressure. So if it's 1 atmosphere, then when you heat it to the temperature that gives you 1 atmosphere pressure at the surface of the liquid, then it'll start to boil. And there's a boiling green liquid. I don't know what that is. Probably food coloring in water. All right. There's the definition of boiling point. Now, normal boiling point has a special, the boiling point, it doesn't matter what the atmospheric pressure is, just whatever it happens to be. So the boiling point for water at sea level would be 100 degrees, nominally, 100 degrees Celsius. But in Denver, at a mile high, the boiling point is probably going to be a lot less than that. You know, maybe, I don't know, 90. So do I have that in a table? Some of my lectures do. Yeah, it's coming up in a table. The normal boiling point simply means that this temperature is measured for the boiling point of the liquid at 1 atmosphere pressure. Now, this boiling point changes with elevation because the external pressure determines what forces are opposing evaporation. The higher the pressure external to the liquid, the more heat you need to add to it in order to get it to convert to the vapor phase. So let's see, do they have Denver in there? Salt Lake City is not quite a mile, right? The boiling point is 96 degrees. Okay. Go up to Mount Everest and try to boil a 3-minute egg. It'll come out soupy because not enough temperature. It's only 70 degrees at the top of Mount Everest. So a 3-minute egg you might have to go 6 or 7 or 8 minutes to get it to coagulate. Okay, there's a definition of the boiling point again. What's the vapor pressure of water at 100 degrees if boiling? It has to be 1 atmosphere by definition. If water boils at 100 degrees exactly, the external pressure must be 1 atmosphere. All right, we've been sort of alluding to these forces that are operative in atomics, between atoms and between molecules. But we can divide them into 2 groups. This will work better. Yeah, it works a lot better. So if you've got a molecule, and we're talking about two or more atoms bound together, covalently, actually, the forces that are holding that molecule together are called intramolecular forces. It's kind of, you know what intramural sports are? Right. There were teams are or within the same school, they're battling each other. Intramural, intramolecular. Intermolecular, on the other hand, is between molecules. Okay. Now, which do you think is generally the stronger of the two? Okay, let's say what would happen if intermolecular forces were stronger? The forces between molecules are stronger than the force within the molecule. What's going to happen to that molecule? It's going to get ripped apart, right? So it's the other way. Intramolecular forces must be stronger in order to hold the molecule together for whatever interactions it's undergoing. Okay. These forces can be very strong and they can be very weak. And they can be subdivided. Now we're talking about forces between molecules. What's attracting those molecules? There are various forces that are possible. And for polar molecules, and what I mean by that is they have a permanent separation of charge in the molecule. Now, it's not a complete charge, not like sodium ions and chloride ions. It would be like, well, the water molecule I mentioned earlier is a perfect example. The word I'm searching for here is electronegativity. Each one of the atoms, each one of the elements in the periodic table has a certain attractive force toward electrons. And as a general trend, the attractive force in the lower left is the lowest. And the attractive force in the upper right, fluorine, is the highest. So if you have two of those together in a covalent bond, say fluorine and, oh, I don't know, something to the left of fluorine. Say, I don't know, hydrogen. Let's try that one. Keep it simple. Then fluorine is going to attract electrons much more strongly than hydrogen, but not enough to break the bond. Okay, so we designate it like this, and that shows the positive end. Right? This is a dipole moment arrow. This says this is the negative end. Sometimes we do it like this. Right? That's a Greek delta. It just means a slight charge. Slightly negative on that side, slightly positive on that side. This is permanent. So when these two come together, say we have hydrogen fluoride gas come together, then they're going to orient themselves like this. And that means this is positive, this is negative, and you get an attractive force between the two. It's electrostatic. We can do the same thing with water molecules. All right, it's going to be this way, which means overall, the molecule is polar that direction. So this is the negative side, that's the positive side. When water molecules approach one another, the attractive force is going to be this negative side against this one. So we have another one down here, we get an attractive force. The stronger that attractive force, the higher the more energy required to separate them. So higher boiling points, and so forth. So the interaction then, let me see. I probably have separate slides that are going to talk about these. Yeah, okay. So that's a list of them. Let's start talking about the individuals. This dipole moment, they call it. Moment is a physics term. So don't worry about it too much. It just means that there's a dipole in the molecule. It has a separation of charges. So if you have a dipole-dipole interaction, that causes the molecules to want to attract one another. So when we go back to our kinetic molecular theory of gases, when they approach one another, they don't act just like billiard balls, right? As they get close, if they're oriented so that the negative approaches, then they bounce away more readily. But if they happen to approach one another with the positive side against the negative, they'll attract. And that influences the real behavior versus the ideal behavior. And the greater the polarity, the stronger these forces are. So water has a particularly high attraction for its neighbors. Hydrogen fluoride does also. We can actually have a combination of fluorine and chlorine. So fluorine would be the negative. It's above chlorine. It's more electronegative. So the fluorine would have the slightly negative side. The chlorine would have the slightly positive, and they orient themselves that way. That's a purely dipole-dipole interaction. Dipole of one molecule interacts with the dipole of the other molecule. Now, under special conditions, the dipole-dipole interaction can be extremely strong. And under these special conditions, we have hydrogen attached to some other molecule, some other atom. And if this atom happens to be fluorine or oxygen or nitrogen, then we get a particularly polar bond that gives us very strong intermolecular attractions. And these contribute to what's called hydrogen bonding. It's simply a subgroup of dipole-dipole, but it is very strong. Now, the extra strength can be attributed to the electronegativity of these elements, which is fairly strong. And also to the small size of this hydrogen, which allows them to get close to one another. All right, so if this side is the negative side, this side is the positive side, the closer the negative can get to the positive, the stronger the bond. All right, it's that the inverse square law of attraction. The further away you get, the weaker the force, but it varies by the square of the distance. So if I go from here and this distance, and I go double that distance, I get 1/4 the attractive force. So it works both directions. So since hydrogen is just a proton, right? It's a little thing hanging out there, we can get really close. And that also increases the strength of the force. So there's your water molecule, some artist's idea of the hydrogen bonding. That's why water is a liquid at room temperature. Right? If it followed the same trend as other hydrogen compounds in its group, like sulfur, selenium, tellurium, those H2S, H2SE, H2TE, if it followed their trends, then water would be a gas at these temperatures. Fortunately, it's not. We'd be in big trouble if all the water on the earth just suddenly turned into a gas. So one other characteristic of molecules that exhibit hydrogen bonding have relatively low vapor pressures. because the attractive forces keep them in the liquid phase. It takes more energy to get them apart into the vapor phase. Oh, and there's an illustration of what I was talking about, right? If the trend were followed for the dihydrogen compounds of the chalcogens, then water would have a boiling point of about -7, -80. But it doesn't. Now, let's see, dipole-dipole, hydrogen bonding. What about molecules that, or atoms for that matter, that are nonpolar? We mentioned that earlier. You guys missed that part of the discussion, but I'll give it to you again. If you have a molecule that's definitely nonpolar, and the example I used earlier was nitrogen gas, right? That cannot be polar because both nitrogens are pulling equally on the electrons in the bonds. So, but we know that this is, excuse me, this is a gas at room temperature. But we know if we cool it down to -195, then we can turn it into a liquid. So how do we explain that? In order to be a liquid, there has to be some attraction between the molecules, right? Hold them together. So if we go back to the kinetic molecular theory of gases, the forces holding these nitrogen molecules together to make a liquid must be very weak, because cooling them down reduces their kinetic energy. If their kinetic energy is reduced below a certain level, then the weaker forces can take over and can hold them together. And these forces are identified as London dispersion. I don't think that's London, the London city. I think it's London person who came up with the idea, or was at least credited with it. So what are the London dispersion forces? Well, in any atom or any molecule, these electrons are not static. They're always moving, some form or fashion. And the chances are always there for instantaneous distribution of electric charge unevenly in the molecule or on the atom. So if that's the case, then for an instant, we may get this negative side and that positive side. Just for a split second. And for any other molecules close to them, the influence is that this positive attracts electrons and makes that negative. And that leaves this one positive. Now we have attraction. And like I say, it doesn't last for very long. This is temporary. It seems to be it seems to be stronger for larger molecules, because the probability of distributing unevenly electron densities in a large molecule, the probability is higher. Or even for atoms, is true. Say if you have, if we look at, let's see, let me erase this. If we want to remove variabilities of different atoms in molecules and size of molecules, we can look at the noble gases. Say neon, argon, krypton, xenon. That's enough. Let's see, 1, 2, 3, 4. Helium. Let's do helium too. Okay, if we look at the boiling points of each one of these, which are going to be very low temperatures, we know that the boiling point of helium is going to be 4K. I'm not sure what the others are, but their boiling points increase in this direction. So the larger the atom, the higher the boiling point, because the larger atom allows for uneven distribution of electron density. So the instantaneous charges can be more prominent for this one than that one, and more for that one than this one, so forth. Smaller the atom, the less likely to have those London dispersion forces acting. That's just more evidence. Oh, there it is. Were you looking ahead and you saw it was coming? Huh? So let's see. Oh, they're given in degrees C. 269. Yeah, add 4K would be minus 269 Celsius. And then we increase as you go down. They've actually got radon in there. Kind of hard to mess with radon because it's radioactive. And the other example is the halogens, right? Fluorine, chlorine, bromine. Bromine is the biggest one, so it's going to have a higher boiling point. Chlorine, in fact, bromine's a liquid at room temperature. Chlorine's a gas at room temperature. Fluorine's a gas at room temperature, but it has a much lower boiling point. And that's due to size. Okay. So there's the strongest of the intermolecular forces. But they're still, even the strongest are weaker than the intramoleculars. Okay. It's very simple. If it was the other way around, molecules get ripped apart. So which one has the stronger intermolecular forces? Well, water, of course, because of hydrogen bonding. Okay. Let's see. We did Lewis dot structures, didn't we? Okay, good. Let's erase these. There. What we're trying to show here is that the structure of the molecule contributes to its boiling point. In other words, if we have the same molecular formula, H6O, I think, is it? Yeah. This could be represented by this molecule, which is ethanol, right? Or it could be represented by this molecule. It has the same molecular formula. And this is dimethyl ether. So which one has the higher boiling point? This one. Because there you have the potential for hydrogen bonding. Whereas here you have a nonpolar molecule, and the only thing that holds it together is London dispersion forces. So the boiling point here is higher. Okay. Am I getting close to the end? Yeah, okay. When I see that concept check, I say, probably getting near the end. I'll finish early. Which gas would behave more ideally at the same conditions of pressure and temperature? When we say behave ideally, which one acts more like a billiard ball, right? Which one has the lower intermolecular forces operating? The one that's nonpolar, right? Carbon monoxide is slightly polar. in this direction. Whereas nitrogen, of course, is nonpolar. So the stronger forces would be between the carbon monoxide molecules, and that would influence its behavior away from ideal. So nitrogen would be the more ideal. It would behave more ideally. And there's a black and white explanation. When we talk about elastic collisions, right? They probably covered that in physics, even in high school, I think. Elastic versus inelastic collisions. 100% elastic collision is one where the two objects come together and they leave with the same kinetic energy they came in with. Momentum is always conserved. Mass times velocity, right? It's always conserved. But an inelastic collision will eat up some of the kinetic energy. So when they come together, a 100% inelastic collision is where they come together like two big chunks of clay and they stick together. So the one that has the more momentum will force the other one in that direction. So ideal behavior, completely elastic collisions. Okay. So let's take a look at these concept questions and then we'll be done. See if we got anything out of this discussion. These things over here, if you go back and look at the video, you'll see if you want to completely describe the physical characteristics, the physical behavior of a gas, you need to know pressure, temperature, volume, and the number of moles. And that will allow you to physically describe the gas and its behavior. Okay, to hide some helium-filled balloons for a birthday party, you decide to place them in a chest freezer. Okay, when you retrieve them, you obviously haven't had one of my classes and you're disappointed that the balloons are deflated. If you've had our class, then you know that's expected and that they will return. As they warm up to room temperature, they return to their original size, okay? What gas law is demonstrated in this scenario? Well, you've got temperature and volume. You guys weren't here for that. Temperature and volume relationship is Charles' law. So Charles' law, and what happens to the kinetic energy of the helium during the warming process? The kinetic energy has to increase in order to put pressure, force on the latex and expand the balloon. So the kinetic energy increases due to Charles' law, and that's D. Okay, last one. A gas water displacement experiment is set up and it's determined that 0.812 grams of gas displaces 300 milliliters of water. The atmospheric pressure is 750 millimeters of mercury. Temperature of the water is 20 degrees. Partial pressure of water is 18 millimeters of mercury. Determine the molar mass of the gas using ideal gas law. Okay, this is a good problem. It's complicated, right? So we have to break it into pieces. Let's work backwards. If the question is, what's the molar mass of the gas? In order to determine the molar mass, which old school is molecular weight, we need to know the mass of the gas and the number of moles represented by that mass. Okay? So we need to know what's the mass of the gas. It's given to us, 0.812, 0.812 grams, okay? We need to find out how many moles that represents. Okay, so that's where the other information comes in. So we got this mass of gas displaces 300 milliliters, 350 milliliters of water. All right, let's draw a picture. we're producing this gas from a reaction over here. And we're sending it over here, like this, and this is water. Except we have a graduated cylinder here, and we got bubbles. So we got, let's say, it fills down to here. And this is 350 milliliters, correct? Yeah, it displaces 350 milliliters. Now, why did I put it all the way down here? Because if it's up here, there's a differential in pressure, and that influences our calculation. So you want the level to be exactly the same as this water level. Okay, atmospheric pressure is 750 millimeters of mercury. So atmospheric pressure is 750 millimeters of mercury. Okay, temperature of the water is 20 degrees. And the partial pressure of water in here is 18 millimeters of mercury. Okay, let's see, I've got everything I need. All right, except for the ideal gas equation. All right. So if we want to find out this number of moles, we can use this equation. The ideal gas equation. We just solve it for moles, and that's PV over RT. So we know what the volume is. It's 350 milliliters. But remember, R is equal to 0.08206 liter atmospheres per mole K. So the volume is not in liters. The volume needs to be 0.350 liters, 350 milliliters. Okay. Temperature, we know what the temperature is, but it has to be in K because the constant is in K. So it's 20 plus 273 equals to 93 K. All right. Let's see. Temperature, volume, R. We need to know what's the pressure of the gas. What's the pressure of the gas in here? Well, the pressure is actually the same as atmospheric because we got these levels at the same place. So the pressure inside is the same as the pressure outside. This is total pressure is equal to 750 millimeters of mercury. But that, excuse me, that is equal to our gas that was produced from the reaction plus water vapor because it bubbled through the water. So we've got two gases in there giving us that pressure. Okay, so Dalton's law of partial pressure says that's equal to the pressure of the water vapor plus the pressure of our gas. What's the pressure of the water vapor? Where is it? Didn't I write it down? Oh, here it is. 18 millimeters of mercury. So the pressure of our gas is equal to 750 minus 18 to 732 millimeters of mercury. 732 millimeters of mercury. That's not in atmospheres. How do we get it to atmospheres? Divide by 760. 760 is 1 atmosphere. So if we divide this by 760, then we got volume, temperature, pressure, volume, pressure, temperature. That's a constant. We can solve for N. So Let me go ahead and calculate this one. 732 divided by 760 is 0.963 atmospheres. Okay. So now we can plug in our numbers and find out how many moles. So pressure is 963. Volume is 0.350 liters. R is 0.08206 liter atmospheres per mole K. And temperature is 293. Okay. Okay, so we can find out how many moles that is. Let's see, 35, 0.08206 and 293. And I get 1.402 times 10 to the minus 2 moles. Now we got all we need. We got 0.812 grams and 1.402 times 10 to the minus 2 moles. So we divide that into 0.812. And I get 57.9 or, yeah, 0.9 grams per mole. And the closest to that one is, oh, worked it out. There it is. I went to all that trouble and there it was. That's good practice. Let's see. There's our moles. And there's our answer. Grams per mole. So it takes a lot of work, I'll admit. But if we start with what do we need and do we have what we need to get it? This is where I start molecular weight. And then I say, all right, now I know how to get there. All right, I think that's it. Yep.